So Jessica sent me an email and I responded, but I apologize for the angst you may have had there. I know I told you last Wednesday that I was going to make an assignment because we still had, the Wednesday lecture and the Monday lecture. But I decided not to, especially in light of two people didn't turn in the last homework assignment. I figured maybe I should just let people get a little comfortable and then we'll move forward again. So I did just post the final physics homework assignment. This week we'll end this week and a half, whatever. We'll end our physics, and then we'll have a test on physics and start in with chemistry. So I think it's on Friday. I've got the syllabus right here. Maybe I have the syllabus here. No, I don't have the syllabus here.
I can't remember. Are tests made of the potential test questions?
They're half from the potential test questions, okay. Yes. So it's not 100%, but it's half. So there is a homework assignment due next week. There's a test next week. Like I said, I think it's Friday, but it could be Wednesday, so we have to check on that.
Is it this Friday?
Excuse me?
Is it this Friday?
It would either be a week from Friday or a week from today. So we are going to finish chapter 5 and starting with chapter 8. Our lab this week is a lab covering chapter 5, Archimedes' Principle. Our lab next week will be from chapter 8. So getting right into it, let's make sure we get connected up with WooClap. And I did not reset, so it says 5 people already connected because it has you from last time.
The exam's on Friday.
It's on Friday? Okay, thank you.
This Friday?
A week from Friday.
Okay, I was going to say.
Yeah, that would be a little short notice. I mean, you had the whole semester, but still it's good to remind. Okay, so assuming you're connected, here's our first question. 2 people are drinking soda using straws. Do they suck the soda up? Could they drink soda this way on the moon? So it's 2-part question. Part number 1 is, can they suck it up? Part number 2 is, could they drink soda through a straw on the moon? We have 3 answers. 4 answers.
I don't have my laptop on.
Okay, you don't have your phone either?
I didn't log it in. It's dead. So.
Oh, okay. Then we'll stop at 4. Okay, so the answers we got were 2 people said yes and yes. 0 people said no and yes. 1 person said no and no. And 1 person said yes and no. So we have not good agreement, and that's fine because unlike almost every question I've asked you, this is one where I didn't prep you for how to think about this and answer it. This was one for you to answer based on what you think. So when you drink from a soda, what do you think is happening? Once again, you can be wrong. I'm asking what you think. I'm not asking what's the correct thing. What do you think is happening? Why does the soda go into your mouth? What?
Because you're sucking.
But why does that make it come into your mouth?
The pressure. The force.
Okay. It has to do with force and pressure. What aspect about them?
That's a good
And
question.
working together.
They always work together.
So there's the pressure of the soda in the cup.
Okay, well, things that we have learned. We've learned that pressure has to be 0 or greater. You can't have a negative pressure. And pressure is force over area. So since the pressure pushing down on the top of the straw, on the fluid inside the straw, is always going to be greater than 0, you're always pushing the fluid down from the top of the straw. Now, if that was all that was going on, you could never drink through a straw. Because, of course, if you have a pressure in that straw that's making force pushing the water down, it should move away from it. Or in this case, the soda. But there is also atmospheric pressure. Remember, atmospheric pressure is pushing on you right now. What direction is that atmospheric pressure pushing?
Down.
Sideways.
What the heck?
In. It's always pointing into a surface. Remember, the force of pressure, this is an important aspect. Force of pressure is always pointing in to an object. So atmospheric pressure is pushing this direction on this part of my nose, this direction on this part of my nose, and so on. It's always pushing in. If you've watched something like the original Total Recall with Arnold Schwarzenegger,
No.
at one point he gets ejected into Mars's atmosphere. The atmosphere of Mars has a pressure that's 1/100th the air pressure here, which means fundamentally that Mars was pushing in on his body with 1/100th the amount of force that we normally have. And so in the movie, they have his eyes start bulging out of his head because air pressure pushes in on our eyes. Now, through accidents, we actually know that wouldn't happen, but you wouldn't have things like your saliva would boil away. It'd be really weird. Yeah. Okay, so, excuse me?
Just, I can't believe that your saliva would actually boil.
Well, it has nothing to do with hot. It has to do with pressure. Boiling occurs when the vapor pressure of the liquid is greater than the atmospheric pressure. Since the atmospheric pressure is so low there, unless you get close to absolute zero, the vapor pressure is greater than atmospheric pressure, it boils. So it's a pressure effect. You never think about that because you always are here on Earth. But we have this amazing thing called the pressure cooker, or the common version that we have today, the Instant Pot.
Right.
And it allows you to cook at a higher temperature because it pressurizes so the water boils at a higher temperature. Okay, so back to this. Atmospheric pressure is pushing on the water, or on the soda in the picture. So, as a practical example, on the top of this soda here, if pressure is always making a force pointing in, what direction is the force applied by atmospheric pressure on the top of that soda? Down, that's right, because down is the inward direction. So atmospheric pressure is pushing in, but then the atmospheric pressure, well, what's happening to the pressure as you go lower in the water?
It gets higher.
It's higher, that's right. And then you come back up the straw and it gets lower. But because atmospheric pressure is pushing on that water, the atmospheric pressure is also pushing the water at the bottom of the straw up. And if the pressure at the bottom of the straw is bigger than the weight of the straw, well, the force that you get from that pressure is bigger than the weight of the stuff in the straw and the force pushing down the top, then it has a net upward force. So what you have is, if you look in the straw itself, you have pressure 1 here. Thank you for doing that. Pressure 1 there. Pressure 2 here. And then you have the material in there. If you change from pressures to forces, you have a downward force 2 is equal to pressure 2 times the area. And upward force 1 equals pressure 1 times the area. And a downward force of gravity is equal to mg is equal to rho times height times area times g. If you want to, this height times area is the volume. That last part doesn't matter to us. What matters is if the net force is up, then it's going to accelerate upward. So when you are, quote, sucking on the straw, you're lowering the pressure of the air above the fluid. And when you lower that pressure, then the downward force is smaller. There's still a downward force. You're still pushing the fluid down, but you're not pushing it down as hard as air is pushing it up. And so the atmospheric pressure pushes the fluid into your mouth. So you're not pulling it in, you're lowering the pressure so atmospheric pressure can push it in. So of course, we know we can drink on Earth. Do you suck the soda up? I would say no. No, you don't suck it up because you still have a reduced air pressure. So I would go with one of these two to start with. Then we have the second half. Could you drink like this on the moon? You could try. Would it work?
No,
No, it would not. Why wouldn't it work?
because the pressure down isn't there, the double pressure down.
Well, the pressure up isn't there. There's no atmospheric pressure there. Since there's no atmospheric pressure, there's nothing to push it into your mouth. So you could go as much as you wanted. It's not going to work. So the correct answer was no and no. I wish you got a cookie. Sorry to make you sad. All right. Pascal's principle is somewhat related to that question. Pascal said that if I change the pressure in one place on a continuous fluid, that's a fluid without any gaps, any bubbles, that the pressure increases by that amount everywhere. And we use this for things like hydraulic lifts. You probably have gone to the car place to have like your tires changed, and they put on a lift and they raise the car. How does that work? They have a little pump with some hydraulic fluid, and they pump that fluid in a little tube that's, maybe half a centimeter in diameter or smaller. But then it goes into a ram, as we call it, that has a big area. So you have a big area on one side and a small area on the other. Now, pressure is force over area. So on this side, you have pressure equals force 1 over area 1. On this side, you have pressure equals force 2 over area 2. If the pressures are the same, so I increase pressure one place, increases everywhere. The pressure is the same on the side with a small area, the force is going to be small. But the side with a large area, force is going to be large. So it's a type of simple machine where it's amplifying the force. But just like with the simple machine, you can't do more work than you put into it. And so the amount of fluid, the volume that you put in has to be the same on both sides, which means a whole lot faster flow on the small side. So the key to a hydraulic lift is shown in this figure. You have a different area. How is it possible for a 10 kilogram mass to balance a 500 kilogram mass? You have different areas, so even though you have the same pressure, and we could, if we knew what the area A was, we could calculate the pressure because pressure is force over area. So if A is equal to, let's say 10 centimeters squared, and we had, area A. I didn't make the graphic, so I can't take that blame. My pressure would be, what's the force on the left-hand side? It'd be 10 kilograms times 9.8 meters per second squared, because force is mass times G. Then divide it by my 10 centimeters squared, and that would be equal to 9.8. And look at the crazy units. You got kilograms, I forgot to write kilograms, meters per centimeter squared, second squared. Those are kind of crazy units, right? It's more fun to write it as newtons per centimeter squared, but usually we would convert it to per meter squared. But there's pressure. Now, if we go to the other side, we have the same pressure, but we have 50 times the area. So what is the force on the other side? Right, on the other side, force 2 is equal to pressure times area 2. That's just taking this equation and solving it for force. And so that's going to be 9.8 newtons per centimeter squared. times 50 times 10, so 500 centimeters squared. And of course, you multiply those through, and you have 500 times 9.8, whatever, that'd be 490. Now, 4,900? Does that work? So it'd be 4,900 newtons that we're lifting with this mass that only has a weight of 98 or 980 newtons. 98? Okay. I'm really good at math here. 98 newtons is lifting 4,900 newtons. So that's Pascal's principle. You increase the pressure one place, it increases by the same amount everywhere in the contained fluid, and it's the key to our hydraulic lifts. And here's just a slide showing the calculations I did in a much cleaner fashion. And this is a practical application to show you how you could use an air compressor to lift a car, compressing the air to make the pressure here in the reservoir. Final thing on fluids. With fluid flow, sometimes you have, like, think about water in a pipe. You go from a big pipe to a small pipe. If you have water flowing through here and it goes into a smaller pipe, what's naturally going to happen to the speed of the water? It speeds up. It speeds up here, so it's faster here. And it's slower here. Our body does this all the time. When you feel stressed, one of the responses your body does is it constricts arteries. What does it do if it constricts the artery? It makes it so it has a smaller area, and then the blood is going through there faster, right? Well, why would your body do that? When God designed us wisely, why would that be part of our design? Well, increasing flow doesn't calm you down. But what happens is when you restrict the flow, or when you make this smaller, it's harder for the blood to flow through here. And it makes the pressure here go up. The pressure here doesn't go up. The pressure here goes up. And so if the pressure here goes up, then you're going to have more pressure pushing blood into the tissue, and it helps you to get oxygen to your tissues better. And so why is that important? Because you need oxygen to metabolize things and make your muscles work. So with this fluid flow, we have Bernoulli's principle, which is really cool. And I'm going to start with the demonstration on this because you've got to get this in. I have lots of favorite demonstrations, but this is one of them. So if I have my blow dryer, which I have disconnected the heating element so we won't have any, hot air blowing around here. If I blow this over the paper, over the top of the paper, do you know what's going to happen?
The paper's going to move on the bottom.
It's going to move. So let's turn this on. Okay, so it moved. How did it move? Well, compare the position of the paper now to now. Okay, so when I blew this over, it went up, right? So if it went up, in terms of forces, what does that mean?
The force of pushing upward.
Well, I have a force of air pushing on it from the bottom. What direction would the force of air pressure on the bottom be pushing? This goes back to the first question. What direction is the force of air pressure on me?
In.
In, because it's always going into the surface. So on the bottom, what direction is into the surface? Up. What about the direction of the force of air pressure on the top? It's going to be down because the surface is horizontal, or upward. So normally, gravity makes this fall down. You have the same force down and up due to air pressure. When I blew air over the top, it came up. I didn't change the gravitational force of the paper. So what could account for the paper coming up when I blow air over the top? There's only two forces acting on gravity and air pressure. So what about the air pressure?
It's higher.
Higher where?
Top.
If it's higher on the top, then I have more force pushing down. So it had to be higher on the bottom. So blowing air over the top must have lowered the pressure on the top. And that's what Daniel Bernoulli discovered, that the faster you have a fluid flowing, the lower the pressure gets. Question, Jessica? Go back a slide. Thought so. Stopped working again. So, according to what we saw, and as explained by Bernoulli, the faster the air is flowing, the lower the pressure. Now, I am going to now take a ping pong ball, and I'm going to blow air in this ping pong ball. It's levitating. Hooray. Why is it levitating? Okay, air pressure. In this case, air molecules were coming up faster on the bottom, hitting it, bouncing off, making higher pressure on bottom, and holding it up there. Because it would have fallen due to gravity if it wasn't for that higher pressure on the bottom. Question, Vanessa?
This has nothing to do with what you're doing right now. So whenever you push a ping pong ball, like with your finger, why does it come back? You know what I mean?
Nope.
Like you have it. No, don't do it. Don't do it. I won't catch it.
It's a ping pong ball. It's not going to hurt you if you don't catch it. Okay.
Like, if you push down like this, like you flick it, you know what I mean? It's not, no. Okay.
See, you perfectly
You go
caught it.
like this, why does it come back?
Oh, you spun it. And so you have friction with the spinning ball, just like a car tire makes the car move.
Okay.
Okay, so, yes, that was unrelated, but still interesting and still physics. So doing this again, I didn't start in the right place, so it bounced real. But now, what's odd now? And notice the ball is not over my stream of air anymore. It's off to the side.
You're spinning it and like the air keeps pushing it upwards, even though there's only a little bit.
Now, spin would have an effect like that. It actually wasn't spinning. You couldn't tell from back there.
Oh.
But spin would. That's how, in baseball, they throw a curveball. They put spin on. Because of the spin, you get different air pressures on one side and the other, and it makes the ball curve. So that definitely would have worked. But in this case, the air was flowing, and excuse me, if the air is flowing at an angle, so we have the air flowing like this, and I put the ball in that flow of air, here's the ball. The forces on that ball are going to be, of course, and I'm only going to show vertical forces, force of gravity downward, and then I have force of air pressure above and below. So force of air top, force of air bottom. There's also horizontal forces, but I'm just focusing on the vertical. So typically, the force of air top and force of air bottom are equal, and it falls because of the force of gravity. But here it wasn't falling. So since it wasn't falling, what does that tell you about the forces of the air on top and the forces of the air on bottom? The force on the bottom had to be greater. Based on Bernoulli, that means that, well, if the force on the bottom is greater, that means the air pressure at the bottom is greater, right? And based on Bernoulli, that would mean that the air speed is greater on the top of the ball than on the bottom of the ball. So what happens is, you bring it off to the side, the ball starts to fall. But as it starts to fall, most of your air is going to deviate to go over the top of it, right? Because it's falling out of your stream. But then you only have the low pressure above it and not below it. And so if the low pressure is above and not below, it gives you the situation where you have a net upward force due to air pressure. So Bernoulli's relation explains how I was able to have my blow dryer at an angle and still have the ball stay up in the air. I'm not going to do anything with that slide. We're not going to talk about laminar versus turbulent flow. So we do have another WooClap question. What happens to the internal water pressure in a narrowing pipe of moving water?
Can you change? It just now changed.
Okay.
But it wasn't changed for like 7 seconds.
So when it constantly is getting narrow, or
Well, if you have a pipe that gets narrow and you have water constantly flowing through. So what happens to the internal pressure of water when it goes from here to here? So we start at A, we end at B. Okay, we have 3 and 1 with our answers. I am failing.
is it unchanged?
No. Well, one person's right. Pressure.
Neat.
I mean, it's good that you're right. But we don't want
Good job,
other people to feel bad.
Jessica.
Oh, it's fine.
I got you.
Yeah, I mean, It's fine. I'm not gonna be mad
Oh,
at
I did it backwards.
Okay, so
Okay.
you have water flowing through, and in the first part, it's going slower. In the narrow part, it has to be going faster. Would we all agree with that?
Yeah.
And so according to Bernoulli, when the speed is faster, the pressure is lower. So the pressure downstream of that nozzle is going to be lower than the pressure upstream. So could you explain now why the pressure here at B is lower than the pressure at A?
Because it's building up.
No.
It narrows more, and then that's when it's like finally releasing.
That works. That works. The one I'm looking for is what Annabelle was saying. It's going faster here. And because it's faster, Bernoulli's relation says it's lower pressure. But that was still correct what you said, Jessica. I don't want you to say no. Practical applications. Tornadoes. My weather station said there's a 1% chance of a tornado today. I'll take those odds. I would go to Vegas and I would bet lots of money we're not having a tornado today. You can give me 100 to 1 odds. Has anyone actually been in a tornado? Really?
Been very close.
Yeah, I've been close. I was in Lincoln when we had the Halong tornado, which is, I don't know, what, 20 miles away. That's as close as, well, actually, that's as close as I've
You
been
mean like
now.
inside of it, or like from here to the door?
Last year at the end of the school year, Amy and I were walking around Holmes Lake when there was a tornado in the other side of town. We saw it. Yeah. It was a little bit, there was a circle cloud above us, but it didn't form a tornado, so we're good. We were dumb. Amy was having the time of her life, by the way. One of the problems that occurs with the tornado is the roof flies off of a house. Because in a tornado, wind is blowing fast. But what does Bernoulli say results if you have the wind blowing at a high speed?
It's creating pressure,
Creating low pressure.
not pressure.
So the pressure is lower when the wind is blowing. So you have these roofs, and of course the roof is generally made so it won't fall into the house. You hold it up. You don't worry so much about holding it down, right? And so you have a lower pressure on the top, but inside the house you have still air. So you have atmospheric pressure inside the house and you have a lower pressure outside. And so the air pressure difference pushes the roof up off the house. Now, of course, you might say, well, why don't we just open the windows in the house? Yeah, exactly. There's another problem there. Sure, you keep your roof, you just don't keep anything inside the house.
Yeah.
So,
I
sorry,
Go
it's
ahead.
gonna be a random question, it's kind of related, but not really. Does insurance, when a tornado comes through and demolishes all your belongings, does insurance cover that?
Yeah.
It actually is going to depend on your insurance and the coverages you
That's what I
have.
thought, because I know like a lot of people didn't have flood insurance when the flood came through.
Yeah.
Okay.
And so, yeah, they charge you extra to cover acts of God.
How nice seems about right in America.
Yeah, most of the time they don't, like they might come to your house but not the stuff lost in it.
Okay.
Cause
Okay.
unless one of that stuff covered, you need it in.
Last thing on chapter 5, an airplane. We've probably all been in airplanes. When I was in graduate school, I thought it was really funny to explain to the person sitting in the seat next to me how an airplane flies. Because you become less and less confident the more you understand how the airplane flies.
Oh,
You did that?
I did that.
that is so nice of you. I'm sure you made everybody.
I made lots of friends, you betcha.
As
So,
a kid, you did that?
no, in graduate school.
Can you imagine this kid doing that though?
Yeah, some kid. Kid, you know too much. Okay, so an airplane wing is not symmetric. The top side has this big curve on, the bottom side is virtually straight. Why? Because as it goes through air, the air molecules are basically here, the airplane wing comes and they go up and come down. But the air on the top has to cover a larger distance of skin on the wing. The air on the bottom has a smaller distance. In a practical sense, that means, as measured by the airplane wing, the airspeed on top of the wing is less than the airspeed on the bottom. We just saw that example with my ping pong ball. I was able to hold the blow dryer at an angle and still hold the ping pong ball up because the airspeed over the top was higher than the airspeed underneath. And so that's what's going on with an airplane. Because of that curvature of the wing, you have lower pressure on top and higher pressure on bottom. So pressure top, well, that's very bad. Pressure top, pressure bottom, and those result in forces. The area of the top and bottom is the same. But the pressure is smaller on the top, hence you have a net upward force. And so what we call the lift force is the pressure bottom minus the pressure top. And as long as that lift force is greater than or equal to the weight of the airplane, it flies. In fact, if that lift force is bigger than the weight of the airplane, it rises. If the lift force is less than the weight of the airplane, it falls out of the sky. We call that a wing stall, by the way, when you slow down so that the pressure difference is not big enough to create a force equal to the weight of the aircraft. So when pilots are flying an airplane, they do things to actually reconfigure the shape of the wing a little bit so that you can fly at a high speed and not have too much upward force and go up, and likewise not have too much downward force and go down. Now that's like in a commercial airplane. And in fact, in military aircraft that are designed to go really high altitudes, they have wings that they deform until they're virtually symmetrical at high altitude. Otherwise, they would just go up more. But it's the Bernoulli relationship that allows us to fly airplanes. Or for that matter, sailboats. Sailboats rely on the exact same principle. On a sailboat, you have a sail. I'm not going to draw a sailboat. It'll take you too long. But you have a sail, and it fills up so that one side is outwardly curved, and the air passes basically like this, creating a higher pressure in here and a lower pressure out there, so that you have a net force in that sail that would push you that direction. because of the pressure difference in the air. Notice that the direction of the force is not the direction that the wind is blowing. In fact, it's pretty much perpendicular to the direction the wind is blowing. So with the sail, you set it at an angle, you go forward, you've got to have some other physics going on. That ends our talk about fluids. I'm not going to go through thermodynamics. We've already learned a few things about thermodynamics, like temperature. What is temperature actually telling you about a gas? This is from class on Monday. Temperature is telling you about the average kinetic energy of the molecules, how fast they're moving. Higher temperature, they're moving faster. And so that's an important thing. That's why when you raise the temperature, things tend to expand because they're moving. They bounce off each other harder and push apart. Now we're getting to electricity. Electricity is a second force. Up to this point, the only force we've explicitly talked about was the gravitational force. We have, believe it or not, only 4 fundamental forces. Those 4 forces are gravitational force, the electromagnetic force, and then the strong and weak nuclear forces. The strong and weak nuclear forces are only relevant inside the nucleus of an atom or in that range of sizes. So there's only 2 forces relevant to us: the gravitational force and the electrostatic force. So the discovery of electrostatic force comes from experiments like this. This here is rubber, but the original experiments were using amber. No one here speaks Greek, do you? Okay. The Greek word for amber is electron. Everything with electricity comes from that Greek word for amber, because the original discovery, you take an amber, because electron is amber in Greek. If you don't speak Greek, you're not going to know that, but you might. Okay, so if you take this rubber rod and you rub it with fur, this used to be one piece, now it's just a whole bunch of pieces, you can do some weird things. So I'm going to bring it up to this little ball, and you can see that the ball reacts to this as I bring it close to it. And so that's the discovery of static electricity. Static means it's not moving, it's stationary. The charge is stuck on here. Now this here is something we call electroscope. It just has some metal. Metal will allow electricity to conduct, to pass around it. And so I'm going to bring this close. And if I bring this close, I can actually touch it. Well, I didn't touch it, I got close enough to it. But you see it responds. Now I bring it away and it still has a little, I'm going to touch it and put a lot on there. So that metal vein has tipped. In terms of forces, what could you tell me? What would forces have to be to make that metal vein tip? It was hanging vertical. What direction would the force have to be on the top of that to make it tip the way it's shown? You'd have to push it this way. So that means there has to be a force between these things that's repelling, that's pushing them away. And so with a force, this is not a gravitational force. I didn't do anything significantly with mass. So it's a new force. And so they call it electric force. And Benjamin Franklin, who was a great scientist, he said, let's call whatever is on the amber rod a negative charge. Why a negative charge? Well, because it turns out if you take a glass rod and you rub a glass rod on silk, my shirt is not silk, look at what happened when I brought that close. When I brought it close, it made it come back. It was clearly affecting it, but affecting it in the opposite way that this affected it. And so they said there must be 2 kinds of charge. So Ben Franklin said the one on the amber is negative. Turns out what's on the amber, we call it an electron because of the Greek word for amber. And so electrons have the negative charge as defined by Ben Franklin. And what was left is called the positive charge. So, why do I do a demonstration like this? So you can see that there is a force And then we can talk about how we describe it. So, fundamental things here. You have positives and positive things. Protons are the positive charge that we interact with regularly. They're the only positive charge we interact with regularly. There are other positives, but it's the only regular one. And the negative one that we interact with regularly is electrons. So as far as you're concerned, charge is either protons, pro because positive, like I am pro, I don't know what I'm pro. I'm pro Union College. I'm positive about Union College. So that's why it's called a proton, because it has a positive charge. And then the electrons have a negative charge. Rules about attraction and repulsion. When I had touched my amber rod to this, the amber rod had excess electrons, excess negative charge. Why do I know that? Because that's how Ben Franklin defined it. Those electrons apparently repelled other electrons. So like charges repel. Electrons will repel electrons. Protons will repel protons because they're like charges. But when I brought the positive one, it did the opposite thing. Opposites attract. So positive is attracted to negative, negative is attracted to positive. So important rules, opposites attract, likes repel. There are two types of electric charge. With gravity, there was only one type of gravitational charge, mass. But with electricity, there's two types of charge, positive and negative. Move forward. So here you can see examples of positive charges repelling because they are like. Positive and negative attracting because they're opposite. Now our next topic after we finish physics will be chemistry. And chemistry, which initially was a subfield of physics, is studying what's going on with atoms. So we have the periodic table back there with atoms, and we're going to have to learn things about it. Like I told you before, we're not going to memorize the table. We have to learn things about them. But as we understand it, atoms have a nucleus, that is the center region, and that nucleus has two types of protons in it, two types of particles in it. Protons, the things with the positive charge, right? And neutrons.
So are we finally getting into chemistry?
Next week. Well, actually the week after. Next week we finish physics and then we have the test. Neutrons are called neutrons because they're neutral. They're not positively charged or negatively charged. They're neutral. And then we have electrons that are orbiting. So the electrons are negative and orbiting the nucleus. The nucleus has protons and neutrons. So when we get to chemistry, this is going to be really important because we're studying the physics of atoms when we get to chemistry. Oh, come on. There we go. If an atom loses an electron, don't want to cover that. If it loses an electron, it starts neutral. That is, atoms in their basic form should have the same number of protons in the nucleus as electrons orbiting them. But if you pluck off an electron, now it's missing a negative. If you're missing a negative, that means you have one more positive than negative. You have a net positive charge. So if you take an electron off of an atom, then we say it's a positively charged atom. An ion is the term we use for a charged atom. So an atom that loses an electron becomes a positive ion. If an atom gains an electron, then it becomes a negative ion. So ions can be positively or negatively charged. But in either case, they have a charge that's not zero. And then we have two categories that we divide materials up into when we talk about electricity. We have conductors, things that electrons can pass relatively freely through, and insulators where they can't move. Now, conductors and insulators are both made of atoms, so they both have electrons, But in a conductor, the electrons can move, whereas an insulator, they're fixed in place and can't move. Now, in my examples, both my rubber rod and my glass rod were insulators. The electrons could not move. But when I rubbed them, when I rubbed my rubber rod with the fur, I had electrons that went from the fur onto the rubber rod. So you can add charge or take charge away from an insulator, but if you put charge here, it's stuck here. It can't move to another place on the insulator. Whereas with a conductor, if I put the charge here, it can go anywhere through here. Notice I touched this and charge went off onto my body. So a conductor, charge can pass all around it. Insulator, the charge can't move, it's stuck in one place. Most electric conductors are metals. And insulators are pretty much anything that's not a metal. So your tabletop, conductor or insulator?
Insulator.
Insulator. So I can take a 9-volt battery and turn it down on the tabletop, nothing happens. I put the 9-volt battery on my tongue, what happens?
It's gonna hurt you.
It's going to sizzle because electrons are passing across my tongue and they're depositing energy on my tongue. Okay, our last of the Woo Clap questions for today. When you brush Fido, your dog's fur, and scrape electrons from it, the resulting charge on the fur. So what happens to the first charge if you scrape electrons off of it? Okay, things were better this time. If we scrape electrons off, it starts with a charge of 0. You remove charge that is negative. So 0 minus a negative number. So let's put just like -5, just to put an example of a negative number. 0 minus a -5 is equal to a +5. So, hey, we got a fifth person. You must have connected up.
Yeah, I finally got it to work.
So it's going to leave behind a positive charge on Fido's fur because electrons, negative particles, were removed from Fido's fur when you rubbed it. Now, practical problem. Your friend is sitting there, just got their headphones on and singing along while you're trying to study, and you're really frustrated. So you want to make them, think about you a little. So you walk around and rub your feet on the carpet. What's happening when you walk around rubbing your feet on the carpet?
Charging up yourself.
You're charging up yourself. How?
No, you can less better friction. Yeah.
Okay, you have electric charge that is being moved from the rubber. Well, the rubber of your feet is acting like the rubber there. It's collecting electrons from the carpet. So you're getting more and more negative. And then you come to your friend and you go, and what happens?
They get shocked.
They get shocked. They get shocked because you built up a negative charge in your body and then you transferred it to them. That's what a shock is transferring the charge. Okay, we are out of time, so that's where we shall end today.